Most of us are aware of the commonly spread misconception that we use our brains at a certain percentage, and that gradually increasing the percentage to which we use our brains will result in profound effects like in the movie Lucy, where a street drug called CPH4 enhances her ability to do anything imaginable, from being able to see microscopic chemical reactions occurring to acquiring Jedi-like superpowers.
Don't move.
I need to talk to you alone.
And I need you to put your hands up, please.
Now, obviously, this claim holds no truth. We actually use 100% of our brain 100% of the time, not 10% as the myth goes. The nervous system, including the brain, is relatively poorly misunderstood within the scientific community. This is especially so in comparison to other branches of science that have more answers than questions, which isn't the case in neuroscience. To begin, the neuron is the building block of all neuroscience, and is, in a nutshell, a site for neurochemical messages to be transferred. In a sense, it could be thought of as an incredibly massive highway hosting billions of cars delivering packages from one point to another continuously. This picture shows the basic anatomy of the neuron. Like all things biological in nature, the structure of the neuron supports its function, which is again a message relayer. A neurochemical signal is collected through the neuron's dendrite. The cell body integrates the signal and generates an outgoing signal to the axon, where it travels next. The signal would then pass through the branch-like axons and out the axon ending, where it is released for another adjacent neuron to receive again through its dendrites. This process repeats itself millions of times through chains of neurons until the signal reaches its destination. Using muscle contraction as an example, the signal would stop at a muscle fiber as it stimulates the muscle to contract. The brain has two hemispheres, simply called the left and right hemisphere. Because of the specific way the neurons are wired in our nervous system, the right side of the brain controls the left side of the body, and vice versa. The brain is further categorized in four lobes: the frontal, parietal, temporal, and occipital lobe. The frontal lobe is responsible for logical thinking and decision-making. The temporal lobe sits adjacently behind the frontal lobe, under the parietal lobe. It is responsible for functions such as hearing and memory. It also serves as a language center, and is the reason why you are able to understand what I'm saying. The parietal lobe is essentially a sensory lobe in the sense that it regulates most of your senses, most notably touch. It's interesting to note that your parietal lobe also enables you to experience proprioception. It's better to demonstrate what proprioception is before defining it. To do so is simple. Close your eyes and wave your arms around randomly. The quote-unquote sixth sense you get by somehow knowing the exact spatial position of your hand is because of proprioception. The occipital lobe is the backmost lobe and is mostly responsible for sight and understanding what you are seeing. The brain actually makes the best guess on what you're looking at instead of automatically knowing. Most of the time it does as well. You are currently looking at a computer monitor or some sort of screen because you see it, and your occipital lobe registers it as such. However, the occipital lobe should not be taken as perfect. The easiest way to prove that it isn't is through optical illusions. When the occipital lobe isn't sure of what it's seeing, the brain tries to fill in the blanks, and these guesses may sometimes fool the brain into seeing something that reality does not actually mandate. Neuroscience has had a rough history in the past. Egyptians pulled the brain out with an instrument to better preserve a corpse to become a mummy. During these times, many conditions that would now be associated with the brain would always be explained simply with discontent with the soul, and that evil spirits must have lived in the patient's head. A hole was cracked into the patient's skull in hopes of releasing the bad spirits out. A procedure called a lobotomy became common in the early 20th century, and it wasn't too different than the Egyptian operation. It involved inserting a blunt instrument into a patient's eye socket and into the frontal lobe, where neural pathways were purposefully destroyed. The intent of the operation, which was pioneered by Dr. Antonio Egas Moniz, was to relieve symptoms of mentally ill patients. He later went on to win a Nobel Prize, but around 50,000 lobotomies were performed in the US alone before the procedure was banned. Today, modern neurosurgery is still evidently risky, but infinitely more safe and precautious than it was in the past. Much of neuroscience has to do with chemistry, especially with neuronal pathways that require sodium and potassium ions to carry out electrical signals. This is the sodium-potassium exchange pump, which is an important part of carrying out these electrical signals. 3 sodium ions bind to the protein receptor shown in the middle with 1 ATP molecule. The ATP molecule completes the reaction so that the protein receptor opens up, letting the sodium ions outside the cell to create an electrical charge. This reaction is done mainly in the axon of a neuron. Without chemistry, every neurochemical reaction and neurotransmitter would simply not exist.